Welcome to Hart und Trocken. My name is Dirk Schiborn, and in this video I want to talk about limits of functions. When analyzing a given function, a typical step is to examine what happens to the function values f of x when the independent variable x approaches some certain points, like for instance singularities, which are points where the function is not defined, or when the independent variable x approaches plus or negative infinity. In this video, I will work through a couple of examples, show you how we solve this problem, and show you in which kind of problems we might run into. So thanks for tuning in and enjoy! Suppose we have some function f of x, and we want to think about what happens to that function if x tends to some specific value x0. In a broader sense, x0 can be both a number, like -3, 0 or pi, but it can also be plus infinity or minus infinity. Of course, plus and minus infinity are not numbers. So let's pick one specific example, like -3. We would like to know how the function values of f behave when we let x tend to -3. Let's start with very simple examples. That is the constant function f of x equals 1. What happens to its function values if x tends to -3? Well, obviously they are 1 and stay 1. So the limit of fx if x tends to -3 is 1. This is the function fx equals x plus 3 squared. What happens to its function values if x tends to -3? Well, obviously, as x tends to -3, the function values f of x tend to the function value of -3, which is 0. So we can write that the limit of f of x if x tends to -3 equals 0. So why was that so easy in this example and the previous example? The answer is because both functions are continuous functions and both functions are defined at -3. So we don't have to think much about converging sequences of function values. We simply plug in x0 into f and evaluate f at x0. Recall that continuity means that we can interchange the limit operator and the function. So we can write this, which means that lim of f of x equals f of lim of x. So the more interesting cases are those where x tends to values where the function f is either not defined or not continuous, or if x tends to negative or positive infinity. Now we display both functions from our previous examples, which we call g of x equals 1 and h of x equals x plus 3 squared. Now we build a new function from those two, which we call f and which is the quotient of g and h. However, we don't draw its graph yet. We rather want to think about first what happens to the function values if x tends to -3. The first thing we note is that f is not defined at -3, because the denominator is 0 at -3. So in contrast to the previous examples, we can't simply plug in -3 into f. To figure out what happens, let's have a closer look at this expression. The numerator is 1 and stays 1, no matter which value we choose for x. The denominator, however, tends to 0 when x tends to -3. So because the numerator is constantly 1 and the denominator goes to 0 when x tends to -3, the fraction, that means f of x, tends to infinity as x tends to -3. But the important question is, does it tend to plus or does it tend to negative infinity? The answer to this question depends on the question from which side the denominator approaches 0, from the negative side or the positive side. If it approaches 0 from the negative side, the function values will tend to negative infinity. If it approaches 0 from the positive side, the function values will approach positive infinity. Usually, this depends on from which side x approaches x0, in this case -3. That means from the left-hand side or from the right-hand side. However, in this case, the denominator is a squared number. Being a square, it is always positive, no matter which value we choose for x, and therefore no matter from which side x approaches -3. Consequently, f of x approaches positive infinity both if x comes from below or from above negative 3. We therefore write f of x tends to positive infinity when x approaches negative 3. Drawing the graph of f, we find that our result is correct. In many problems, the graphs of the functions we are considering are not available. Typically, we are given the function like f of x equals 1 over square root of x plus 3. In order to understand the function better, we first analyze its domain. Because the expression under the square root must not be negative, we have to exclude all numbers which are smaller than negative 3 from the domain. However, for x equals negative 3, the denominator assumes the value 0, which is why we additionally have to exclude negative 3 from the domain. So we replace the greater than or equal to sign by a greater than sign. Now, because the function is continuous on its entire domain, it is rather boring to think about its behavior near points which are within the domain. The interesting points are the points at the boundary of the domain. So let's look what happens at negative 3. As the domain of f lies at the right-hand side of negative 3, we can only consider sequences of x which approach negative 3 from above. In order to denote that we restrict ourselves to sequences from above, we usually write x to negative 3 plus with a little uppercase plus symbol. Now we have the following line of argumentation. If x approaches negative 3 from above, it follows that x plus 3 approaches 0 from above. Consequently, we have that square root of x plus 3 also approaches 0 from above. We therefore have that f of x, which is 1 over square root of x plus 3, approaches positive infinity, as x approaches negative 3 from above. Now the other boundary of the domain of f is plus infinity. What happens to f of x if x approaches plus infinity? To figure that out, we can build a similar line of argumentation. If x goes to plus infinity, it follows that x plus 3 goes to plus infinity, from which follows that the square root of x plus 3 goes to plus infinity. But that means that the denominator of the fraction tends to plus infinity, and it follows f of x goes to 0 as x tends to plus infinity. In many cases, lines of argumentation like this work well and lead to the desired result. However, there are functions where we run into problems. Such a function is, for instance, f of x equals sine of x over x. Obviously, this function is defined for all real numbers x except for x equals 0. When we think about the behavior of the function values when we approach 0, say from above, we think about the behavior of the numerator and the denominator separately. Doing that, we find that sine x tends to 0 from above as well. The denominator x, however, also tends to 0 from above. So we run into a situation which we may call 0 over 0. In such a situation, we cannot continue our line of argumentation. So what do we do now? We probably need to dive deeper in order to analyze the limit of f of x as x tends to 0 from above. However, fortunately, we don't have to put much work into that, because there's a nice little rule which helps us to cope with situations like these. According to its creator, it is called de L'Hopital's rule. We will present and discuss de L'Hopital's rule in the next video. So that's it for this video on limits of functions. Thanks for watching and see you next time.